Quantum mechanics is a branch of physics that studies the strange and counterintuitive behavior of matter at the atomic and subatomic level. It delves into the very fabric of reality, exploring how particles that are unimaginably small interact in ways that defy our everyday experiences. In the quantum world, things aren't so clear-cut. Particles can exist in multiple states at once, and their properties are not defined until they are observed. This is a realm where the rules of classical physics no longer apply. Imagine a tiny world where things can be in multiple states at once, like a coin spinning in the air, both heads and tails at the same time. This concept is known as superposition, where particles can hold multiple positions or states simultaneously. This is called superposition. It's a fundamental principle of quantum mechanics that allows particles to be in a combination of states until they are measured. Another mind-boggling phenomenon in quantum mechanics is entanglement. This occurs when particles become interconnected in such a way that the state of one particle instantly influences the state of another, no matter the distance between them. Imagine two of these spinning coins magically linked. When you observe one coin and it chooses to be heads, the other coin instantly becomes tails, even if they're miles apart. This instantaneous connection is what makes entanglement so fascinating and perplexing. When you observe one coin and it chooses to be heads, the other coin instantly becomes tails, even if they're miles apart. This phenomenon has been experimentally verified and continues to challenge our understanding of the universe. Quantum mechanics might seem bizarre, but it's been proven time and again through experiments. Scientists have conducted numerous tests to confirm the predictions of quantum theory, and the results consistently support its strange and counterintuitive principles. It's this very strangeness that quantum computers exploit to perform calculations in ways unimaginable for classical computers. By harnessing the principles of superposition and entanglement, quantum computers can solve complex problems at speeds that would be impossible for traditional machines. Quantum computers are a new breed of computers that harness the principles of quantum mechanics to solve complex problems that are impossible for even the most powerful classical computers. Imagine a computer that can be in multiple states at once, exploring countless possibilities simultaneously. That's the power of quantum computing. Unlike classical computers that store information as bits, which can be either 0 or 1, quantum computers use qubits. These qubits can exist in a superposition, representing both 0 and 1 simultaneously, allowing quantum computers to perform computations exponentially faster. Classical computers are like bicycles, great for everyday tasks. They are reliable, efficient, and perfect for handling routine activities that we encounter daily. Just as a bicycle gets you from point A to point B on a well-paved road, classical computers excel at tasks that require straightforward linear processing. They store information as bits, which can be either 0 or 1, like a light switch being on or off. This binary system is the foundation of classical computing, enabling it to perform calculations and process data in a clear step-by-step manner. They process information sequentially, one step at a time. This means that each operation must be completed before the next one begins, much like an assembly line in a factory where each worker performs a specific task in a set order. Quantum computers, on the other hand, are like spaceships. They represent a leap into the future, capable of navigating complex and uncharted territories with ease. While classical computers are bound by the limitations of linear processing, quantum computers break free from these constraints. They use qubits, which can be both 0 and 1 at the same time, thanks to superposition. This unique property allows quantum computers to handle multiple possibilities simultaneously, vastly increasing their computational power. It's like a light switch being both on and off simultaneously. This duality is what gives quantum computers their extraordinary ability to process vast amounts of data at once. This allows them to explore many possibilities at once, making them incredibly powerful for specific tasks. For example, they can solve complex algorithms and perform parallel processing at speeds unattainable by classical computers. Imagine searching for a specific grain of sand on a beach. This analogy helps illustrate the difference in efficiency between classical and quantum computing. A classical computer would have to examine each grain one by one. This method is time-consuming and labor-intensive, much like sifting through sand grain by grain. A quantum computer could analyze all grains simultaneously, finding the right one much faster. This ability to process information in parallel makes quantum computers a revolutionary tool for tackling problems that were previously thought to be unsolvable. Qubits are the building blocks of quantum computers, analogous to bits in classical computers. However, unlike bits, which can only be 0 or 1, qubits can exist in a superposition, representing both 0 and 1 simultaneously. Imagine a spinning coin that is both heads and tails at the same time until you stop it and observe it. That's superposition. This unique property allows qubits to store and process information in a fundamentally different way than classical bits. This ability to be in multiple states simultaneously is what gives quantum computers their immense computational power, enabling them to tackle problems that are intractable for classical computers. Section 5. Quantum gates, directing the quantum dance. Just like classical computers use logic gates to manipulate bits, quantum computers use quantum gates to control and manipulate qubits. These gates perform operations on qubits, changing their state and allowing for complex computations. Imagine a choreographer guiding dancers through a series of movements. Quantum gates act like choreographers, directing the qubits through a series of operations, creating a carefully orchestrated quantum dance. These quantum gates are crucial for performing quantum algorithms, which are sets of instructions that tell the quantum computer what to do with the qubits to solve specific problems. Section 6. Quantum algorithms, the language of quantum computers. Quantum algorithms are sets of instructions specifically designed to be run on a quantum computer. They leverage the principles of quantum mechanics, such as superposition and entanglement, to solve problems in ways that classical algorithms cannot. Think of quantum algorithms as recipes for quantum computers. Just like a recipe guides a chef in preparing a dish, a quantum algorithm guides a quantum computer in performing a specific task. These algorithms are crucial for unlocking the potential of quantum computers, enabling them to tackle complex problems in fields like medicine, material science, and cryptography. Section 7. Shor's algorithm, cracking the code. In the realm of quantum computing, Shor's algorithm stands out as a groundbreaking development. This algorithm, named after mathematician Peter Shor, has the potential to revolutionize the way we approach encryption and data security. One of the most famous quantum algorithms is Shor's algorithm, which has the potential to break the encryption methods commonly used today. Traditional encryption relies on the difficulty of factoring large numbers, a task that classical computers struggle with due to the immense computational power required. It efficiently factors large numbers, a task that would take classical computers billions of years. The sheer speed and efficiency of Shor's algorithm come from its ability to leverage the principles of quantum mechanics, allowing it to perform calculations at an unprecedented rate. Imagine trying to find the prime factors of a very large number. For a classical computer, this would involve checking each possible factor one by one, a process that becomes increasingly time-consuming as the numbers grow larger. A classical computer would have to try each possible factor one by one. This brute force method is not only slow but also highly inefficient, making it impractical for very large numbers. Shor's algorithm, using the power of quantum computing, can find the factors exponentially faster. By harnessing quantum bits, or qubits, it can process multiple possibilities simultaneously, drastically reducing the time needed to find the correct factors. This algorithm has significant implications for cryptography and cybersecurity, as it could potentially render current encryption methods obsolete, highlighting the potential impact of quantum computing. The ability to break encryption so efficiently means that data once considered secure could be at risk, prompting the need for new, quantum-resistant encryption techniques. As we continue to explore the capabilities of quantum computing, Shor's algorithm remains a pivotal example of its transformative potential. Section 8. The future of quantum, a world of possibilities. Quantum computers are still in their early stages of development. However, their potential applications are vast and game-changing. Imagine a world with new drugs and materials designed with the help of quantum simulations, revolutionizing healthcare and technology. Quantum computers could accelerate drug discovery, optimize traffic flow in megacities, and revolutionize artificial intelligence. The possibilities are endless, and researchers are continuously exploring new ways to harness the power of quantum mechanics to solve some of humanity's greatest challenges. Section 9. Conclusion. The quantum revolution is just beginning. Quantum computing is a paradigm shift in computing, promising to revolutionize various fields. While still in its infancy, the progress made in recent years is remarkable. As research and development continue, we can expect even more groundbreaking discoveries and applications in the future. The journey into the quantum realm has just begun, and the possibilities are as vast and mysterious as the quantum world itself.